Dear students, in the last class we have studied about the structure of the atom. You know that in the atom electrons are present in the shells, next in the subshells and next in the orbitals. Now these arrangement of electrons, how it is in the atom, let us we study in the today's class. So it is called as electronic configuration. An atom contains as many electrons as its atomic number. If the atomic number of an atom is 8, it contains 8 electrons. If it is 20, it contains 20 electrons, and so on. These electrons are distributed in various shells, subshells and orbitals. The distribution of electrons in various shells, subshells and orbitals of an atom is called its electronic configuration. The distribution of electrons in various subshells and orbitals of valence shell or outermost shell is called valence shell configuration. The electronic configuration of an atom is written as NL raised to x, where n is the principal quantum number. Its value will be 1, 2, 3, 4 if the electron is present in the first shell, second shell, third shell, fourth shell and so on. L is the azimuthal quantum number. L refers to S, P, D and F subshells. X is the number of electrons in the subshell. The maximum number of electrons in the shell is given by the equation 2n square. So, by this we come to the conclusion that K, L, M and N shells can accommodate maximum 2, 8, 18, 32 electrons respectively. The maximum number of electrons in the subshell is given by the equation 2 into bracket 2L plus 1, where L is equal to 0, 1, 2, 3 and so on for S, P, D, F subshells. S subshell can accommodate maximum 2 electrons, P subshell can accommodate 6 electrons, D subshell can accommodate 10 electrons and F subshell can accommodate 14 electrons respectively. The maximum number of electrons in any orbital is to accommodate 2 electrons of opposite spin. Hence, S subshell contains only one s orbital, P subshell contains 3 p orbitals, D contains 5 d orbitals and F contains 7 f orbitals. The 3 p orbitals are given as px, py and pz. The 5 d orbitals are named as dxy, dyz, dxz, dx square minus y square and dz square orbitals. And we know there are 7 f orbitals are there which have complicated structures. Now coming to the rules for writing the electronic configuration. There are 5 rules: Aufbau principle, N plus L rule, Pauli's exclusion principle, Hund's rule and then extra stability rule. Coming to the first one, Aufbau principle. Aufbau is a German word meaning to build up or construction. Aufbau principle states that the orbitals are filled up with electrons in the increasing order of their energy. So, this is shown in the figure. The order of increasing energy of the orbital is shown as 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, and so on. The question is, it is in the diagonal way, but it is not like the aberrations. So, why it is so? This can be explained based on n plus L rule. Suppose if I say the increasing energy of the orbital is 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4s, 5s, 5p, 5d, 5f. If it is like this, the n plus L values are different, and if we write diagonally, the n plus L values are different. So, that's what we are going to study here. The relative order of energy of different orbitals can be determined with the help of n plus L value. N means principal quantum number and L means azimuthal quantum number. For example, 2p orbital. Here n plus L is equal to n value is 2, p, L for p is 1, 2 plus 1 it is 3. For 3d orbital n is 3 and for d subshell L is 2, 3 plus 2 it is 5. For 4s orbital n is 4, L is 0, 4 plus 0 is equal to 4. N plus L rule states that the orbital having the lowest value of n plus L has the lowest energy and hence is filled up first with electrons. When two or more orbitals have the same value of n plus L, the orbital with lower value of n is lower in energy and hence is filled up first with electrons. Consider 4s orbital. Here n plus L is equal to 4 plus 0 is equal to 4. And 3d orbital n plus L is equal to 3 plus 2 is equal to 5. This shows that 3d orbital is having higher energy than 4s. Hence, electrons first enters into 4s orbital first and then 3d orbitals. Consider 2p orbital. Here n plus L is equal to 2 plus 1 is equal to 3 and 3s orbital. Here n plus L is equal to 3 plus 0 is equal to 3. Both have same n plus L value. In such cases, the orbital with lower n value is filled first and then the other. Hence, 2p orbital is filled first and then 3s orbital. Based on n plus L rule, the order of increasing energies of the orbital is like this: 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s and so on, where the n plus L value is gradually increasing 1, 2, 3, 4, 5 and so on. Here also I have shown the Aufbau principle, how the electrons enters into the various orbitals and orbitals with increasing energy. Here in another way I have shown the diagram, the 1s orbital, 2s orbital, 2p is having 3 orbitals. So, the next comes 3s, 3p, 4s, 3d, 4p and so on. So, this is another way of showing the electronic configuration and the orbitals in the respective. Now coming to the another one, the Pauli's exclusion principle. In 1925, Pauli proposed the exclusion principle. They are as follows. No two electrons in an atom can have all the four quantum numbers the same. This is one way of explaining the Pauli's exclusion principle. The others are the two electrons in the same orbital will have identical n, l and m but must have different spins, maybe either plus half or minus half. The third way of explaining, electrons with same spin repel each other and occupy different orbitals, and if they have to occupy the same orbital, they must have opposite spins. The fourth way of explaining, the capacity of each orbital is to occupy two electrons of opposite spin. These are the various ways where the Pauli's exclusion principle can be stated. Pauli's exclusion principle has no mathematical explanation, but it has an experimental facts. The orbital has lower energy if the paired electrons in it has opposite spins. The two electrons in the orbital with parallel spins gives higher energy to the system, hence not possible. I can explain this Pauli's exclusion principle taking an example of the carbon atom. The carbon atom contains the 6 electrons, where we can write its electronic configuration as 1s2, 2s2, 2p2, and these electrons can be distributed in this way where I have shown. And for the first electron, the n, l, m and s will be the 1, 0, 0 plus half, and the paired electron the same n, l and m, but s is minus half. Similarly, the electrons in the 2s will be 2, 0, 0 and s is different plus half and minus half. The electron in the 2px, here the n is 2, l is 1, m is 0, for px orbital, and s is plus half. For py orbital, n is 2, l is 1, m is plus 1 and s is plus half. These quantum number values proves the Pauli's exclusion principle, that is, no two electrons in an atom can have all the four quantum numbers the same. So, this is what I have explained in this slide also. Coming to the next one, the Hund's rule of maximum multiplicity. Hund's rule can be stated in the following ways. Whenever the orbitals of nearly equal energies are available, the electron enters into all the orbitals singly first and then pairing takes place. The orbitals of nearly equal energies are present in p, d and f subshells because these subshells have the different orbitals. P subshell contains 3 orbitals, D subshell contains the 5d orbitals, the F subshell contains 7 f orbitals, and these orbitals have almost equal energies. In such cases, the Hund's rule is applicable. The another way we can explain, in an atom no electrons pairing takes place in the p, d or f orbitals respectively until each orbital of the given subshell contains one electron. The different way, another way of explaining the Hund's rule is the unpaired electrons present in the various orbitals of the same subshell should have parallel spins. All these statements represents the Hund's rule. Electrons in half-filled orbitals of the same subshell experience less interelectronic repulsion when they have parallel spins than opposite spins. Now, here I have shown the Hund's rule explanation. Now, if I take an atom carbon, its atomic number is 6, electronic configuration will be 1s2, 2s2, 2p2. Here, the 1s contains the 2 electrons, hence the the opposite spins. 2s also have opposite spins, and when the 2 electrons are present in the 2p, these 2 electrons will go into the px and py orbitals singly. Similarly, in the nitrogen, the 3 electrons goes to px, py and pz orbitals singly first. When we come into the oxygen, 4 electrons are there in the 2p. So, 3 electrons go single and the 4th will get paired up. In case of the fluorine also, the 3 electrons goes singly first and then the other 2 electrons gets paired up. This is what the explanation regarding the Hund's rule. Coming to the last rule called the extra stability rule. It states that half-filled and completely filled subshells are found to be more stable. Hence, elements tries to attain this configuration as far as possible. To the example, chromium atomic number 24. Its outer electronic configuration should be 3d4 4s2. But by taking one electron from 4s2, so 3d also becomes half filled, 4s also becomes half filled. So this leads to the extra stability. Hence, chromium is more stable than the other elements. Therefore, its electronic configuration becomes not 3d4 4s2, it becomes 3d5 4s1. Similarly, the copper also, the outer electronic configuration will be 3d10 4s1, but it is not 3d9 4s2. Once again, the explanation for this is the extra stability rule. Here I have shown the Hund's rule and how the distribution of electron takes place according to the Hund's rule. Here also I have shown the Hund's rule for various the elements as well as ions. This slide gives once again the 3 rules of Aufbau principle, Pauli's exclusion principle and Hund's rules of maximum multiplicity. Students, go through these things, and if you have any doubts, you can ask me through the WhatsApp. But to write the electronic configuration, all these rules you have to remember. Thank you.